Hello and welcome to this physics video, Simple Harmonic Motion, U8.SHM3. Our objective today is to explain the relationship between simple harmonic motion and uniform circular motion. And we also have something to do after that. So let's get started. First off, let's just define what simple harmonic motion and uniform circular motion is. So first off, we have simple harmonic motion is the vibrations about an equilibrium position where the restoring force is proportional to the displacement from equilibrium. And the uniform circular motion is the motion of an object that is traversing a circular path with a constant speed. So knowing that now, let's look at these diagrams right here. What we have here is a circular path, and we have the point P on this path. Now, if you have a circular motion, you can look at it from a different point of view. If I were to project a circular motion and look at it from a different perspective, I would see this, just vertical motion, oscillating up and down to the equilibrium point. So really what's happening here is the x-axis is acting as the equilibrium position, and when it goes above the axis and below, it's oscillating. A sine graph easily shows this. When it crosses the x-axis, that's where it goes through the x-axis and it reaches the equilibrium position. Now also it says that the restoring force, there has to be some type of restoring force, and that restoring force is actually going to be the velocity. Now it says up here that it has to have a constant speed. Now, good thing for us, speed is scalar, so it's just the magnitude, but velocity is vector. It has magnitude and it has direction. So when it travels to the below the x-axis becomes negative, and above the x-axis becomes positive, there's this restoring force that allows it to keep going and make this centripetal force around this position. So that's really how simple harmonic motion and uniform circular motion are related. So now we have to calculate the period and frequency of an object spring system. And to do that, we need this equation right here. The period of a mass spring system is simple harmonic motion. What this equation says is T, which is period, equals 2 pi times the square root of m over k. M is mass and k is spring constant. So knowing that, let's solve a problem. What is the period and frequency of a mass spring system when the mass is 24 kilograms and the spring constant is 6 newtons per meter? Round to the nearest whole number. So let's get our equation down here. And we have m, which is 24, and we have 6, which is our k, or spring constant. And knowing that, we can just say that 24 divided by 6 is 4, so it would be 2 pi times the square root of 4, and the square root of 4 is 2, so it's 2 pi times 2, and let's just put that into our calculator. And we get this value right here. Now, the question does say round to the nearest whole number, so we are just going to round that to 13. So that is the period. The period of this motion right now, one complete cycle, is 13 seconds. But it also asks us for the frequency, and all you have to do for that is take the inverse of that number. So it would be, let's see here, 13 to the negative 1. And we would get this. That means in 1 second, this is how much of that cycle that would be completed. So let's see here. Frequency. And here we go. The frequency, it completes 0.8 of its cycle per second. So there we did it. Using this equation for the period and simple harmonic motion, we can calculate the period as well as the frequency. Thank you for listening.